Okay, let's see another one of these. We're going to solve this separable differential equation. Doesn't appear to be at first, so a little bit more work required for sure. X y to the fourth plus the quantity y squared plus 2 times e to the negative 3x dy over dx equals 0. Okay, so before we can even begin, we need to put it into the form of a separable differential equation. So what's that going to look like? Let's subtract the x y to the fourth. And then a couple things. Let's divide by e to the negative 3x. And let's divide the y to the fourth over this way. So our aim is to get all of the y's on the left and get all of the x's on the right. And we've pretty much done that at that step. Let's talk about that one more time. So when we divide by e to the negative 3x, notice you divide by a negative exponent, and we could turn that into a positive exponent here on the right side, and then dividing by y to the fourth over here, like so. So y squared plus 2 over y to the fourth dy over dx equals negative x e to the positive 3x. And now what are we going to do? We're going to move this dx here to the right and then integrate both sides. So we have integral y squared plus 2 over y to the fourth dy equals, and I'm just going to move that negative out, negative integral x e to the 3x dx. And we're well on our way to solving this differential equation. At this point, the integrals are a little bit more challenging. And so we got to think, okay, how are we going to perform each of these? So I've got some my notes here. So on the left, we're going to split the fraction. So what I mean is, we're going to take y squared over y to the fourth plus 2 over y to the fourth, and we'll be able to get that integral without too much strain. On the right side, though, x e to the 3x, we need integration by parts. Okay, let's focus there. So here's the setup for this integration by parts. We're going to take u to equal x. We're going to take dv to equal e to the 3x dx. So that means du equals dx, and that means v equals 1/3 e to the 3x. And then we're going to do what we do on the left side as well. So here's what I have so far. On the left side, y squared over y to the fourth is y to the negative 2. Plus 2 over y to the fourth, well, that's plus 2 y to the negative 4. So we still have to integrate this. Equals, and here's our integration by parts here on the right, the negative out in front. And then we've got v times u, or u times v, 1/3 x e to the 3x. Minus v du, and I move the 1/3 out, minus 1/3 integral e to the 3x dx. Okay. And we'll just keep going. Integrating y to the negative 2 is negative 1 over y. 2y to the negative 4, well, that's negative 2/3 y to the third, well, y to the negative 3, but we'll just tuck that y to the third underneath. Remember, we don't need the plus c here on the left. We keep going. Let's see, this is just kind of copied down, and then this antiderivative, well, another antiderivative of e to the 3x would be another 1/3 e to the 3x, and so that makes minus 1/9 e to the 3x, and then we'll distribute our negative. So we've got negative 1/3 x e to the 3x plus 1/9 e to the 3x, and we put our plus c here on the right side with the x's. And we notice, okay, we've done it, but that is an implicit solution because it's not solved for y. One thing we could do to make this look a little bit cleaner is multiply everything by maybe 3 or even by 9. And you notice, let's go for negative 9. That's a good idea. We got several negatives. So multiplying each term by -9 makes this look just a little bit nicer. Nothing wrong with this one, but I think we could all say this is slightly better. 9 over y plus, and then the 2/3 times -9, right? Plus 6 over y to the third, and still multiplying by -9, 3e to the 3x minus e to the 3x plus c. Oh, okay, so we did multiply the c by -9. It's easy to think, well, what about the c? So you multiply -9 here, 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 but not. We did multiply the c by -9. But what's an arbitrary constant multiplied by -9? Just another arbitrary constant. So we don't need to change it. And then you might think, well, if this was positive, shouldn't this at least be negative? No. Because what if c itself is negative? Right, so we can still, if we multiply an arbitrary constant by -9, it's still an arbitrary constant plus c. So this looks a little bit better. Okay, and we notice, well, it's still implicit. We still haven't solved for y, but yeah, we're not going to solve for y here. That's just too much. We're going to be content with our implicit solution in a case like this. So you might be wondering, all right, when you do, say, homework, how would you know to stop with an implicit or when to continue for an explicit, or maybe like on a quiz or something, is on a test? If I want an explicit, if I want you to answer as an explicit, I'm going to tell you in the directions. I'm going to say solve and answer as an explicit solution. If it does not say to answer as an explicit, then I'm going to be perfectly happy with an implicit or an explicit. They're both solutions. Implicit solutions are not inferior to explicit in a mathematical sense. Now, usually we prefer explicits if we can get them. But those are going to be the times that I tell you to answer as an explicit. So if all it says is solve, then either one perfectly okay. And that's what we had here. Okay, let's keep going. Okay. As a matter of fact, here we go. This example asks us to solve the IVP. Remember, that's the initial value problem. And we will answer as an explicit solution. Okay. Now, this is the way differential equations and their initial conditions are usually presented. So we've got the differential equation here, comma, and we've got an initial condition right there, which will help us solve that IVP. So the differential equation is x squared y prime equals y minus xy. Now we're going to put all of our focus here for most of the problem. We're only going to go to the IVP towards the end to wrap things up almost. But most of this problem, 90% or more, is trying to solve that differential equation. That's where we begin. When we solve this differential equation, we're going to have a c involved in the solution, and then we go here to figure out the value of that c, and then we'll make sure we answer as explicit. Okay. So looking to this, x squared y prime equals y minus xy. Well, yeah, that doesn't appear to be a separable differential equation just yet, so let's work with it a little bit. How could we work with this to get it to be separable? This is sneaky. Couple things. We do need to rewrite the y prime as dy over dx, because in a little while we're going to multiply that dx to the other side. So we want to think of it this way. On the right side, notice you can factor out the y, right? You can begin to separate x's and y's. So y times 1 minus x. Okay, and then working with that, let's try to get all the y's on the left, all the x's on the right. So we'll divide that y over. We'll divide the x squared over the other way. and we've got 1 over y dy over dx equals 1 minus x over x squared. And then we're going to take that dx and put it over to the right side and integrate. So integral 1 over y dy equals integral. And notice here I'm going to go ahead and split that fraction. So 1 over x squared, x to the negative 2, minus x over x squared is minus x to the negative 1 dx. Kind of setting ourselves up for that integral already. And now let's see how will this work out. Well, 1 over y is the natural log of y. X to the negative 2, well, that's negative 1 over x. You could say negative x to the negative 1, but I prefer it in this form. Hey, we've got minus x to the negative 1. Well, that's really just 1 over x, so that's a minus natural log absolute value x. And then we put our plus c here on the right. Okay, so we have taken all those antiderivatives, integrated both sides with respect to their correct variables. So you could say we found the family of solutions right there. From this point, we have two ways we could go. Neither is better or easier than the other. Once we have the solution, we need to do two things. We need to solve the IVP, so that would be using the initial condition. We need to plug in the x value and the y value, the x and the y, and figure out the value of c. But we're also going to have to answer as an explicit solution. So we've got two choices. We can use the initial condition to figure out the c right here. And then once we have the value of c, then go about finding or isolating the y and answering as an explicit. You could do that. Another way is to do it the other way around. Just try to solve for y as it is here. And then once you have the explicit solution, then go and use your initial condition and find the c in that newly rewritten explicit solution. That's actually the way I'm going to go about it. However, you could easily change the order at this point of the problem. It's personal preference. So I've got that note right here. We could find the explicit solution, solve for y, or we could use that initial condition and find the value of c. But whichever one you do, you're just going to have to do the other one next. You're not making things any easier or harder, whichever way you do it. So I'm going to find the explicit solution because honestly, that is more challenging than finding the value of c, whichever way. So I'm going to do the harder thing first. How are we going to isolate y? So this is the one I'm going to do next. How are we going to isolate y here? And you might say, well, just put both sides into the power of e. Okay, yeah, you could do that, but there's a much better way to do it. And our answer is actually going to come out really, really clean. Okay, so watch and learn. Here's what we're going to do. This first step, it's like, who would think of this? I'm not changing anything except for the c. I'm going to rewrite c as the natural log of the absolute value of c. Now, who would think to do that? Okay, but it's going to play right into our hands this way. So c becomes the natural log of c. If that's an arbitrary constant, so is this. So no problem. That's arbitrary, and now this whole thing is arbitrary. What does that allow us to do? We're going to move this natural log and this natural log to the other side. Like so. And by the way, just ignore what I have going on over here. Okay, so we're going to add natural log x to the left. And you might think we need to subtract natural log c. But again, because it's an arbitrary constant, subtracting it is the same thing as adding it. So let's add it. for reasons that will be clear in a moment. And all that's going to leave on the other side is negative 1 over x. Okay, now that we have all of these on the left and they're all being added, we can combine them all into a single natural log. If we multiply, so we're going to say this is the natural log of the absolute value of c times x times y. Remember your laws of logs. And that really shows you why we didn't want to think of it as subtraction, because subtracting we'd be x times y divided by c. There's no reason to do that. Let's add them all and say c times x times y. Okay, and now here's where we want to put both sides in the power of e. So the e, obviously on the left, cancels the natural log, and on the right we get e to the negative 1 over x. And finally, all we got to do is divide by cx, and we got the y by itself. That is really cool. Y equals 1 over cx, e to the negative 1 over x. And we have found an explicit solution. Very nice. Now it will be very easy to go ahead and do that IVP part with the initial condition. Remember it said y of negative 1 equals negative 1. We're going to apply that to find c. Y of negative 1 equals negative 1. So we've got our x and we've got our y. So let's plug those both in. So we've got negative 1 equals 1 over c times negative 1, e to the negative 1 over negative 1. And if we clean it up a bit, okay, negative 1, this is negative 1 over c, e to the first. And then we'll go back over here. Oh, my mistake. One last line. So what does c equal? Well, the negatives on both sides, and we can multiply the c on this side. So c will just equal e. But we're not done just by finding c. We're going to put that back in to our explicit solution right here. Y equals 1 over ex, e to the negative 1 over x. There's our explicit solution, and we solve the IVP. Why do I have it another version? Well, because we see e appear twice, and we're dividing by e, that's like e to the negative 1. We could combine that with this e, 1 over x, e to the negative 1 over x minus 1. You could answer this way as well. No, splitting hairs there. You can answer either way. Those are both explicit solutions that will fit that initial condition. Now you might be asking, hey, what would this problem look like if we had changed the order of things back at this step? Would they have been any easier? Well, no. If we used our initial condition at this moment, y is negative 1, x is negative 1. Let's just play with it for just a moment to see how it would go. The natural log of absolute value negative 1 equals negative 1 over negative 1 minus the natural log negative 1 plus c. Okay, well this would be the natural log of 1 is 0 equals 1 minus 0 plus c. So we would realize that negative 1 equals c. And we could plug that in. Natural log y equals negative 1 over x minus the natural log of x minus 1. But what does that mean for us? Well, we're still going to have to solve for y here. Right, so we're still going to need, to rethink, right? We'd still say, okay, this is going to be minus the natural log of e to get that minus 1. And then what are we going to do? We're going to put these back on the other side. We're going to combine them all. We're still going to end up with the same equation in the end. Right. Like it didn't change anything. It didn't even change the difficulty level. So there you go. Okay, this one was challenging. Solving that for y, that was tough. But hey, now you've seen this trick, right? So we can manipulate that c in certain ways to help us work with the algebra a little bit nicer. All right, let's end this video here.